A seesaw can look perfectly balanced even when the two people on it have different masses. How is that possible? The answer is that equilibrium depends not only on forces but also on torques. In this video, we will discuss the conditions for equilibrium. First, the net external force must be zero, so the object does not accelerate in a straight line. Second, the net external torque must be zero, so the object does not have angular acceleration. By the end, we will use these two conditions to solve a seesaw problem and find both the position of one child and the support force from the pivot. An object is in equilibrium when its acceleration is zero. The first condition for equilibrium is force equilibrium. The net external force on the object must be zero. In two dimensions, this means the horizontal forces must add to zero, and the vertical forces must also add to zero. If the net force is zero, the object does not accelerate in a straight line. It may be at rest or it may be moving at a constant velocity. This is just Newton's second law applied to the special case where acceleration is zero. Forces can still act on the object, but they must be balanced. Now let us compare two types of force equilibrium, static and dynamic. This person is in static equilibrium because he is motionless and the forces on him add to zero. There are two main vertical forces. Gravity pulls downward and the normal force from the ground pushes upward. Since the person is not accelerating vertically, the upward normal force balances the downward weight. The net vertical force is zero. There are no unbalanced horizontal forces shown, so the net horizontal force is also zero. Static equilibrium means the object is at rest and remains at rest because the forces are balanced. An object can also be in equilibrium while moving as long as its velocity is constant. This car is in dynamic equilibrium because it's moving with constant velocity. Constant velocity means the speed and direction are not changing, so acceleration is zero. Therefore, the net external force must be zero. Horizontally, the applied driving force is balanced by resistive forces such as friction or air resistance. Vertically, the normal forces from the road balance the car's weight. The important point is that equilibrium does not require the object to be motionless. It requires zero acceleration. So, static equilibrium means at rest with balanced forces. Dynamic equilibrium means moving at a constant velocity with balanced forces. Now, let us see why force equilibrium alone is not always enough. Here we have an ice hockey stick lying flat on ice. Two equal and opposite horizontal forces are applied along the same line. Because the forces are equal in magnitude and opposite in direction, the net horizontal force is zero. Vertically, the weight of the stick is balanced by the normal force from the ice. So the first condition for equilibrium is satisfied. The net external force is zero. In this case, the stick remains stationary. The forces not only cancel in translation, but they also do not create a net turning effect, so the stick is in static equilibrium. But the same two force magnitudes can fail to produce equilibrium if they are applied at different points. The forces are still equal and opposite, so the net force is zero. That means the stick will not accelerate as a whole in a straight line. However, the forces creates a turning effect. The stick rotates, and in fact, it has angular acceleration. This is the key lesson. Net force equal to 0 is necessary for equilibrium, but it is not sufficient. To have full equilibrium for a rigid object, we must also require the net torque to be 0. So an object can have no translational acceleration but still rotate if the torques are not balanced. That brings us to the second condition for equilibrium, torque equilibrium. To avoid angular acceleration, the net external torque on the system must be 0. This means the clockwise torques must balance the counterclockwise torques about the same pivot point. An external torque is a torque produced by an external force. When calculating torques, the pivot point or axis of rotation must be the same for all torques in that equation. This point matters because changing the pivot changes the lever arms. For a given torque equation, choose one pivot and stay consistent. Now we can state the full conditions for equilibrium together. For a rigid object to be in equilibrium, two conditions must be satisfied. First, the sum of externally applied forces must be 0. In two dimensions, that means the horizontal forces balance and the vertical forces balance. Second, the sum of externally applied torques must be 0. That means the clockwise and counterclockwise rotational tendencies balance. So for equilibrium, we need both translational equilibrium and rotational equilibrium. This slide gives the checklist we will use in problems. Force balance in each direction and torque balance about a chosen pivot. Let us apply these conditions to a seesaw problem. Two children are balanced on a seesaw of negligible mass. The first child has a mass of 26 kilograms and sits 1.6 meters from the pivot. The second child has a mass of 32 kilograms. We need to find how far she is from the pivot. Part B asks for the supporting force exerted by the pivot. Because the seesaw is balanced, it is in equilibrium. That means the net torque is 0 and the net force is 0. For part A, torque equilibrium is the most useful condition. The first child's weight produces a torque on one side of the pivot, and the second child's weight produces an opposite torque on the other side. For balance, those torque magnitudes must be equal. Before calculating, let us predict the answer. The second child is heavier, so she should sit closer to the pivot than the lighter child. Since the first child sits 1.6 meters away, we should expect the second child's distance to be less than 1.6 meters. Now let us solve part A using torque equilibrium and part B using force equilibrium. Let's first write down given values. M1 is 26 kilograms, R1 is 1.6 meters, M2 is 32 kilograms, and R2 is what we want to find. For part A, let's select the pivot point as the axis for calculating torque. This is a smart choice because the pivot force acts at the pivot, so it has 0 lever arm and produces no torque about that point. Both children's weights act perpendicular to the seesaw, so the angles gives the maximum torque effect. So since theta is equals 90 degrees, sine 90 is 1, so the torque equation will be just the lever arm times the force. Now let's write the torque from the first child, positive R1 W1. If you look at the diagram, the force W1 is trying to rotate this seesaw in the counterclockwise direction. So the torque from that force is positive. And the torque for the second child is negative R2W2. It is negative because W2 is trying to rotate the seesaw in the clockwise direction. The torque from the pivot point force is 0 because the lever arm is 0. Now the net torque is equals to torque 1 plus torque 2, and that is R1W1 minus R2W2. And this have to be equals to 0 for torque equilibrium. Now we can rearrange this equation, so we can send this part to the right hand side of the equation, and we get R1W1 equals R2W2. So we want to find R2, so R2 equals R1W1 divided by W2. Now we can substitute the values. So R2 is equals to 1.6 meters times 26 kilograms divided by 32 kilograms, and this is equals to 1.3 meters. This matches our prediction. The second child is heavier, so she must sit closer to the pivot to balance the seesaw. For part B, we use the vertical force equilibrium. The seesaw is not accelerating upward or downward, so the upward pivot force must balance the total downward weight of both children. The F net in y direction had to be equals to 0, so the pivot point force had to be equals to W1 plus W2, and this is equals to M1 plus M2 times G, and we can substitute the values. So 26 kilograms plus 32 kilograms times 9.8 meters per second square, and this is equals to 568 newtons. So the second child sits 1.3 meters from the pivot, and the pivot exerts an upward support force of 568 newtons. The main lesson is that equilibrium problems often need both conditions: torque balance to prevent rotation and force balance to prevent linear acceleration.